Here's a question that sounds like it has an obvious answer. Could you stop a tsunami with a seawall? A wall is just concrete, a tsunami is just water. Engineers build things. So let's take this completely seriously, run the actual wave physics, and find out exactly how tall, how thick, how deep, and how expensive a seawall would need to be to actually work. The answer is taller than you think, thicker than you'd believe, deeper than seems reasonable, and more expensive than the thing you're trying to protect. But let's be specific.
First, the wave. A tsunami is not a normal ocean wave. A normal wave is surface energy. It churns the top layer of water and moves on. A tsunami is a displacement wave. The entire water column moves from the surface to the sea floor. When a 9.0 magnitude earthquake shifts the seafloor by several meters across hundreds of kilometers of fault line, it doesn't create a ripple, it creates a moving wall of ocean. In deep water, a tsunami can be less than a meter tall and travel at 800 kilometers per hour, fast enough that a jet aircraft could barely keep up. You wouldn't notice it passing beneath your boat. But as the wave approaches shore and the ocean floor rises, the wave slows down. The energy behind it has nowhere to go except up. This is called shoaling, and it is the mechanism by which a barely visible open ocean wave becomes a 15-meter wall of water by the time it reaches a coastline. In the 2011 Tohoku tsunami, run-up heights, the maximum elevation the water reached on shore, exceeded 40 meters in some locations. That's roughly the height of a 13-story building. Japan had seawalls. Some of them were 10 meters tall. The water went over them.
So, let's build a seawall that works. We'll design it for the Cascadia subduction zone, the fault running along the U.S. Pacific Northwest coast, which geologists believe is capable of producing a magnitude 9.0 or greater earthquake. The resulting tsunami would likely produce run-up heights of 20 to 30 meters along the Oregon and Washington coastlines. Our seawall needs to be at least 30 meters tall. For comparison, the Hoover Dam is 221 meters tall, so 30 meters is not structurally unprecedented. But the Hoover Dam is 379 meters wide and holds back a reservoir. Our seawall needs to run continuously along hundreds of kilometers of coastline. Every meter of coastline must be covered, because water finds gaps. The Oregon coastline alone is about 580 kilometers long. Washington adds another 300. We need roughly 900 kilometers of continuous 30-meter seawall. That's concrete, a lot of concrete. A 30-meter wall needs a base roughly 15 to 20 meters wide to maintain structural stability against the dynamic loading of a tsunami wave. Dynamic loading is different from static loading. It's not just the weight of the water pressing against the wall, it's the impact force of a moving wave. The 2011 tsunami exerted pressures of up to 300 kilopascals on structures in its path. That's about 3 times the pressure at the bottom of a 30-meter swimming pool, applied horizontally, instantaneously, across the entire face of the wall. To resist that force across 900 kilometers of wall, you'd need foundations extending 10 to 15 meters below grade into competent bedrock, not just soil, because saturated soil liquefies under seismic loading, which is exactly when you need the wall most. The Pacific Northwest coastline is not uniformly underlain by competent bedrock. In many locations, the foundation work alone is the dominant engineering challenge.
Let's talk about cost. The 400 kilometers of Japanese seawall built after 2011 cost approximately $12 billion. That wall averages about 10 meters in height. Our wall is 3 times taller, more than twice as long, and requires substantially deeper foundations in geologically complex terrain. Scaling conservatively, a Cascadia seawall comes in somewhere between $50 and $100 billion. The entire state of Oregon has an annual budget of about $30 billion. The seawall costs more than Oregon can spend in 3 years on one piece of infrastructure protecting one coastline against one type of event. And here is the final problem. The Cascadia subduction zone earthquake, the one that generates the tsunami our wall is designed to stop, will also be the largest earthquake to hit the Pacific Northwest in recorded history. A 9.0 magnitude earthquake causes ground subsidence. The land along the Oregon and Washington coastline is expected to drop by 1 to 2 meters when the fault ruptures. Our 30-meter seawall, sitting on foundations drilled into ground that just dropped 2 meters, now needs to be 32 meters tall. The earthquake that creates the tsunami also undermines the wall built to stop it. The seawall concept is fine, by the way. Concrete walls are a mature technology. We've completely mastered making things out of concrete. The Pacific Ocean is the part that keeps being unreasonable.